In this lecture, we are going to prove the existence of algebraic closures. We begin with the definition of an algebraic closure. A field extension K over F is called an algebraic closure if two conditions are satisfied. The first is that K is an algebraic extension of F. And the second condition is that K is algebraically closed. In this case, we call K an algebraic closure of F. We have already seen an example of an algebraic closure. We have the complex numbers containing the rational numbers, and in between we have Q bar, which we define to be those complex numbers which are algebraic over Q. And we have seen that Q bar over Q is an algebraic closure. In the case of the rational numbers, we were lucky to have this field of complex numbers to work with. But what about fields like finite field FQ with Q elements, or what about a field like rational functions with, say, complex coefficients, or rational functions with coefficients in a finite field, or fields with multiple rational functions in multiple variables? Each of these fields, it turns out, admits an algebraic closure. And what I'm going to show you in this lecture is a proof that every field admits an algebraic closure. Now, the proof uses a very deep axiom of mathematics called Zorn's lemma. So let's talk about Zorn's lemma. I'll state Zorn's lemma first, and then we'll carefully go over the meaning of each of the terms that appears in the statement. So Zorn's lemma says that if you have a partially ordered set P, where every chain has an upper bound, then P has a maximal element. So that's the statement. Let's now break it down and see what each of these terms that occur in the statement means. So to begin with, let's talk about partially ordered sets. What is a partially ordered set? A partially ordered set is a set P together with a relation less than or equal to, we call it less than or equal to, it's a partial order relation. So P is a set and this is a relation on P, and it must satisfy the following axioms. The first axiom is the axiom of transitivity, which means that if x is less than or equal to y and y is less than or equal to z for x, y, z in P, then x is less than or equal to z. So this is a property that we are familiar with, that the order in real numbers or integers satisfies. And the second property is called reflexivity. So reflexivity, and it says that x is less than or equal to x for every x in P. And the third property is called antisymmetry, which says that if x is less than or equal to y and y is less than or equal to x for any x, y in P, then x must be equal to y. Okay, so these three properties are all properties that you're familiar with. The natural numbers, the real numbers, or the integers all have an order relation which satisfies these properties. But what is more important is what is missing. So it is not true in a partially ordered set. It doesn't have to be true that any two elements are comparable. So any two real numbers, if you're given, either they're equal or one is less than the other, or the other way around. But in a partially ordered set, you could have pairs of elements for x and y such that you neither have x less than or equal to y, nor do you have y less than or equal to x. So this is weaker than the usual notion of order, which then in this context is called a total ordering. So let's look at an example. Let's look at x any set, and let 2 to the power x denote the power set of x. Then 2 to the power x, the power set of x, together with set containment, the relation of set containment is a partial order. Right? Clearly, if a set x is contained in a set y and a set y is contained in a set z, then the set x is contained in the set z. Then secondly, every set is contained in itself. And thirdly, if a set x is contained in a set y and a set y is contained in a set x, then x and y are equal. So the power set of any set forms a partially ordered set under containment. And note here that this is not a total order, because you can find two sets x and y such that neither x is contained in y nor is y contained in x, provided of course that the capital X, the big universal set, has at least 2 points. Okay, and so now we have explained what is the meaning of partially ordered set. So it's like an ordered set but partial, where not any two elements are comparable. Now next we come to the notion of a chain. So let P be a partially ordered set. So we define a chain, a subset C of P, where P is a partially ordered set. Now I'll use this shorthand poset to denote for partially ordered set. So this P stands for partially, O stands for ordered, and set. So poset is just short for partially ordered set. A subset of a poset is called a chain if for all x and y in C, either x is less than or equal to y, or y is less than or equal to x. So what we are saying is that when you take the partial order and restrict it to C, then you get a total order. Let's look at an example, or a special case of the previous example. Consider n to be the set of natural numbers, and let's look at 2 to the power n with set inclusion. So this is a poset, and let box n denote the set as we have in algebra 1, the set of all integers between 1 and n. Then you look at C equals this collection box n belongs to n. This is a subset of 2 to the power n, and C is a chain, because any two elements of C will be of the form m and n, and m is less than or m is contained in n is the same as saying that m is less than or equal to n. So any two elements of C will be comparable. The ordering on the elements of C will match with the ordering of the corresponding integers. So we have also now defined chain, and now it remains to say, well, next I must tell you what does it mean for a chain to have an upper bound. So let's go to the definition of an upper bound. Oops. So if P is a partially ordered set, and S is any subset of P, then an element X belongs to P is called an upper bound of S if S is less than or equal to X for all S in S. So this element X is an upper bound for S, means that it bounds every element of S. So that explains upper bound. In the example, if I take S to be, well, what did we take last time? I called it C. The only upper bound for C is N itself. No other set contains all the subsets that are in C. Okay, so this is the only upper bound. Okay, so now we have also explained what is an upper bound, and there's one last technical term here, which is that of a maximal element. So what is a maximal element? So if P is a poset, S any subset, then a maximal element of S is an element S0 in S such that for any X in P, if X is greater than or equal to S0, or maybe I should say it like this, for any X in S, if X is greater than or S0, then X is equal to S0. So there is no element of capital S other than itself of capital S other than S0 which is greater than or equal to S0. So that's this definition of a maximal element. So we've defined all the terms in this. Let's just look at an example of maximal element. This you would be familiar with if you've done ring theory. So let P be the poset of all set of all ideals in a commutative ring R. Then a maximal element, and let's say we need to tell you what is the partial order, so partially ordered by containment. Actually, I don't want all ideals, I want all proper ideals. All proper ideals. Then the maximal elements of P are precisely what we call maximal ideals. More specifically, if I take P to be ideals of Z, then maximal elements are the ideals P generated by primes. And if I take P to be ideals in Ft, where F is a field, then maximal elements are generated by Ft, where Ft is irreducible. This actually holds in any principal ideal domain. The maximal ideals of a principal ideal domain are ideals generated by irreducible elements. So now we know all the terms that appear in the statement of Zorn's lemma. If P is a partially ordered set where every chain has an upper bound, then P has a maximal element. Let's look at an example where the hypothesis of Zorn's lemma does not hold and the conclusion doesn't either. So take, for example, P to be the set of power set of natural numbers under containment, and let's take S to be n, where n is a natural number. Okay, so in this, of course, this is a chain, and S has upper bound n. Okay, but let's look at now P prime to be a set of all finite subsets of n. So let's look at all sets A subset of n such that A is finite, partially ordered by containment. Then S is still a subset of P. Every set in n, S is finite. So S is a chain in P prime, but we saw that the only upper bound for S in P was the set of natural numbers itself, and so S has no upper bound in P prime. Also, there is no maximal element in P prime. P prime has no maximal element. Because if you were to take any finite subset of the natural numbers, you could always add one more element to it, one more natural number to it, and get another finite subset of the natural numbers. So P prime has no maximal elements. Now let's look at a good example of a maximal element. So let's look at Q bar. So Q bar is a maximal element of the poset P equals E over Q, where E is an algebraic extension. Well, let's just say write E, where E is an algebraic extension of Q. In fact, if you have any algebraic extension of Q, it is contained in Q bar, because Q bar contains all the elements of the complex numbers which are algebraic over Q. And so every algebraic extension is contained in Q bar, and therefore Q bar is the maximal algebraic extension. It itself is algebraic, of course. So now we can come to the statement of the theorem which says that every field admits an algebraic closure. The theorem states that, so this is the existence of algebraic closures, the main theorem of this lecture. Let F be any field then F admits an algebraic closure. There exists an algebraic closure K over F. Now for the proof, before we jump into the proof, so we'll prove it by applying Zorn's lemma. We'll construct a certain partially ordered set of extensions, and we'll show that all chains in that collection in that partially ordered set have upper bounds, and then a maximal element of that partially ordered set, we will show it to be an algebraic closure of F. But we need one slightly technical lemma for that, and the lemma is that if K over F is an algebraic extension, then the cardinality of K is less than or equal to the maximum of Aleph naught, which is the cardinality of the natural numbers countable, and the cardinality of F itself. We've seen this kind of argument when I explained to you that Q bar is a countable set. So basically, if you take an element alpha in K and send it to the irreducible polynomial of alpha, this defines a finite to one function from elements of K to the set of irreducible polynomials in Ft. And the cardinality of the set of irreducible polynomials in Ft, you can show quite easily, is this number here. I'll call it CF, maximum of Aleph naught and the cardinality of F. So I won't give you all the details of this, just think through it. In any case, we'll just use the statement. And now let's go on to the proof. So proof of existence. So to start with, let S be a set with sufficiently large cardinality such that firstly F is contained in S, and secondly cardinality of S is greater than CF. Okay, so its cardinality is strictly greater than the cardinality of any algebraic extension of F. Now we'll define the partially ordered set P. Let P be the set of all field extensions K over F, where K is realized as a subset of S and K is algebraic over F. Okay, and define a partial order by saying that K1 is less than or equal to K2 if and only if K1 is a subset of K2. It's just the containment partial order. And in particular, this would mean that K1 is a subfield of K2. So maybe I should be a little more careful because we talk about sets and sets with the structure of a field. So maybe I'll say if K1 is a subfield of K2 or K2 is an extension of K1. Now I claim that every chain in P has an upper bound. And the proof is the following. So suppose Ki, I in I is a chain in P. Need not be a countable chain, any chain. Then let K be the union of all these sets. I will define a field structure on K. So given X and Y in K, we have X belongs to Ki, Y belongs to Kj for some I, j in I. Now if I is less than or equal to j, then Ki is contained in Kj. And so define X plus Y to be the sum in Kj. And you can also define X times Y to be the sum in Kj. So just define sum and product to be sums and products in the larger of the fields containing these elements. And then because of the fact that our partial order insists that the subsets be subfields, this will give rise to a well-defined notion of sum and product in K and make K into a field. These operations endow K with the structure of a field. Now, I need to show that K is algebraic over F. But this is easy because if you take any alpha belonging to K, then alpha belongs to Ki for some I belong to I. And so, but Ki is algebraic over F, so is algebraic. So alpha is algebraic over F. And so every chain in P has an upper bound. We've proved this. And so the conclusion is, by Zorn's lemma, P has a maximal element. it would typically have more than one maximal element, but has at least one maximal element. Call it, choose one maximal element and call it K0. I claim that K0 over K is an algebraic closure. Since K0 over K is in P, we know that K0 is algebraic over K. So all I need to show is K0 is algebraically closed. Suffices to show that K0 is algebraically closed. So what we need to show is that every polynomial in K0 factors into linear factors. So if Pt belong to K0t does not factor into linear factors, we'll try to get a contradiction. Okay, firstly I want to reduce to the case where Pt is irreducible. If Pt is not irreducible, then you factorize Pt into its irreducible factors. Each of those irreducible factors will not, at least one of those irreducible factors will not be a product of linear factors. So at least one irreducible factor of Pt in K0t is not a product of linear factors. Because if each of these factors was a product of linear factors, then Pt itself would be a product of linear factors. Okay, so we can assume that Pt is irreducible. Just replace Pt by one of its irreducible factors. Now what you do is realize the field extension K0t mod Pt has a subset. So let's call this E. So Pt is irreducible, so Kt mod Pt is a field as a subset of S, with K0 sitting as constant polynomials. With, So we already have K0 is a subset of S, so with K0 sitting as constant polynomials. The reason we can do this is that S has a larger cardinality than K0, because the cardinality of K0 is this cardinality that we've written down here, the maximum of Aleph naught and the cardinality of F. But S has cardinality strictly larger than that cardinality Cf. So then there's enough space inside S to take this polynomial ring and embed it inside S in a way that it puts K0 as constant polynomials. Then E is algebraic over K0. And K0 over F is algebraic, which implies that E over F is algebraic. This contradicts our assumption that K0 was maximal in P. So the proof of the existence of the algebraic closure of any field is a fairly simple application of Zorn's lemma. Well, you have to be careful. We needed to fix this set S so that we don't run into problems from set theory. But that's about it.